At the end of chapter 4, we introduced this idea of an integral. That will be the focus of chapter 5. In section 5.2, we're going to define what an integral means. But first we need a little bit of background information, and that's going to come from this section 5.1. The first thing we're going to discuss is geometrically what it means to compute an integral. And actually an integral is going to be looking at the areas under curves. So with a derivative, it's the slope of a tangent line. So geometrically we're looking at a line, but with integrals, it's an area under a curve. So we're looking at an area. Let's go ahead and look at this curve here in example 1. And let's say I wanted to compute the area under this curve, which is 5 over x. I want to compute the area from x is equal to 1 to x is equal to 5. So I want to look at from 1 to 5. I'm going to have some area. Which would be represented by this highlighted region. The problem is that I don't know how to compute this area. This is not one of the general shapes that we normally have, like a square or a circle or a triangle. There is no geometric area formula for this shape. So instead, what I'm going to do is I'm going to create rectangles because I know how to compute the area of a rectangle and sort of fit it to this region. I'm going to first start with looking at the left endpoints. And I'm going to be using 4 rectangles. Okay, so what this is going to look like is I'll have 1, 2, 3, 4, 5. So I'm going to be partitioning off this area into 4 rectangles. So now what I want to do is I want to create my rectangles. If I use the left endpoints of each one of these intervals that I've created, so let's say I want to use 1 as my first endpoint when I create my rectangle. Then from that point, I'm going to go up to the curve. And then I'm going to make a vertical or horizontal line across, and then I'm going to come down. And that's 1 rectangle. Then I'm going to look at the next left endpoint for the next interval, go up to the curve, draw a horizontal line, and then come down to create another rectangle. Next endpoint, go up to the curve, draw a horizontal line, come down, and I've got my 3rd rectangle. And then my last rectangle would be like so. So what I've done is I've created 4 rectangles because I know how to compute the area of a rectangle. It's just going to be its base times the height. And then you could probably see that this is going to be an overestimation of what my area would be because we have these pieces of the rectangle once I compute the areas of these rectangles. That will mean my estimation is too big. So again, we're looking at the left endpoints of each of these intervals that I made when I partitioned from 1 to 5 into 4 rectangles. So if I was going to compute the area of these rectangles using the left endpoint, so I'll use L for left endpoint, and I have 4 rectangles or 4 intervals. it's going to be the length or base, which in this case is 1, times the height. So the height of this first rectangle is going to be the y value when x is equal to 1, or f of 1. So this area is going to be adding up the area of all these rectangles. So it's going to be the base times the height, plus, when I look at this second rectangle, the base is still the same, it's 1. The height is f of 2. So 1 times f of 2 would be the area of the next rectangle. And again, this third rectangle has a base or a length of 1 and a height of f of 3. So plus 1 times f of 3. Our last rectangle, base is 1, height is f of 4. So again, I'm estimating the area by filling in rectangles whose height is based on the right endpoint in each one of these intervals, these 4 intervals. Okay, so clearly 1 times anything, it's not going to change those values. And my function is 5 over x. So f of 1 would be 5 over 1, or just 5. And I'm going to add that to f of 2, which is 5 halves, f of 3, 5 over 3, and f of 4, which is 5 fourths. So I'm going to just plug this in a calculator. And when I do that, I get 10.42. And then notice that this estimation of that area is an overestimation, because my rectangles are larger than the area between the curve and the x-axis. So let's do the same thing. Let's go ahead and partition, but this time we're going to go ahead and partition it using right endpoints. So again, I'm going from 1 to 5, and I'm going to split this up into 4 rectangles. But this time I'm going to start at the right endpoint for each one of these rectangles. So I'm going to start at 2, go up to my curve, and then draw my horizontal line and come down. Then I'm going to look at 3, which is the right endpoint for this next interval, go up to the curve, draw my horizontal line and come down, and then 4, go to the curve, come across, and then my last rectangle, go up to the curve and come across. So this is the total area that I'm going to be computing with these rectangles. And as you can see, this actually is an underestimation of the area between my curve and the x-axis. When we're looking at the height of these rectangles, it's going to be again the f of x or y value. So the height of my first rectangle is actually going to be f of 2. The second one is f of 3. The height of the third would be f of 4. And then the last one is f of 5. So using our right endpoints of the intervals that we've created, I have 4 rectangles that I'm adding the area up. Remember, this base is still 1 for all of these rectangles. So this is going to be the base times the height or you could look at it as length times width. Oops, sorry, this should be a 2, my bad. And then the next one would be the base, or the length times the width, plus 1 times f of 4, plus 1 times f of 5. So those are the areas of my 4 rectangles. Now 1 times anything, again, I don't need that. So this total area is going to be f of 2, which is 5/2, plus f of 3, which is 5/3, f of 4, which is 5/4, and then 5/5 is just 1. Adding all these up, and again, I'm just going to plug this into my calculator and look at an approximation. 642. And I can clearly see that this is an underestimation because I have all of this area here that's missing from the curve to the x-axis. So going back to the first one, this was an overestimation, and it was 10.42. If I use right endpoints, I get an underestimation. So let's compute the areas of these 4 rectangles in a different way. Let's use, instead of a left endpoint or a right endpoint in each one of our intervals, let's try a midpoint and see what that looks like. Okay, so again, we're partitioning from 1 to 5, and then we're going to create our rectangles, right? Out of these 4 intervals that I've just made. I'm going to be using a midpoint. So this is the point 3/2 or 1.5. And then I'm going to be using a midpoint between 2 and 3 of 5/2. And then between 3 and 4, 7/2, and then between 4 and 5 we'll have 9/2. So I'm going to create my rectangles by going up to the curve, drawing my horizontal line, and then coming back down. So this would be my first rectangle. That would be this piece here. Okay, so let's do our next rectangle. We're going to go from 5/2 to our curve, and then the next one will go 7/2 to the curve, draw a rectangle, and then 9/2 to our curve and draw our last rectangle. So let's just look at the area that we've created with our 4 rectangles. Now clearly it depends on the curve we have. But if you look at this particular partition where we made these midpoint rectangles, notice that we have an overestimation, but we also have this underestimation. So the 2 pieces sort of cancel each other out a little bit, not quite though. So in yellow, what I have is the underestimation, and then we have this overestimation. And it looks like they're going to cancel each other out. If we look at the height of these rectangles, the first one is going to be f of 3/2, and then we have f of 5/2, f of 7/2, and f of 9/2. Now remember, looking at these lengths, or the base, it's still all just 1. So using the midpoint with these 4 rectangles, we get 1 times f of 3/2 the area of the first rectangle plus 1 times f of 5/2, which is the area of the second rectangle, plus 1 times f of 7/2, plus, I'm running out of space, 1 times f of 9/2. So this would be 10 over 3 plus 2. It's going to be 10 over 5 plus 10 over 7 plus 10 over 9. In my calculator, that gives me approximately 7.87. And then when we compare all three values, notice the 7.87, the midpoint, it's between the left endpoint and the right endpoint, and that visually it looks like a better estimation about what this area would be. Now remember, the reason why we're doing this is because the area between the curve and the x-axis is not a regular shape that I have a geometric formula for to figure out what the area is. Go ahead and move on, and we'll be looking at some of the notation when we partition. We're dealing with, right now, we're dealing with what we call a regular partition. And a regular partition is a partition where the base or the length of all the intervals are the same. So notice in our previous example, the base or the length of those intervals were all 1. So in a regular partition on some interval AB, we create these subintervals. And the length of each subinterval is what we call our delta x. That's the distance of x values. It's going to be, you subtract the endpoints and divide by n. So n is the number of subintervals that you have. So the endpoints of your intervals are these x sub 0, x sub 1, and so on. Those are what we call our grid points, and they create our partition of subintervals called a regular partition. If we needed to figure out the kth grid point, it can be found by taking the first point A plus k times your delta x. And here when we talk about our k values, these are just whole numbers. All right, so let's go ahead and look at this curve again that we had on the previous page, and we'll look at all of this notation and we'll discuss what it means with respect to this curve. So again, remember this function is 5 over x, and the interval that we're looking at is 1 to 5. So this would be my A, it's 1, and my B is 5. Now in this particular case, we partitioned it into 4 rectangles. So n is equal to the number of rectangles, which is 4. So the next thing I want to do is I want to find my delta x. So my delta x is going to be the length of each one of my subintervals or partitions. And that can be found by taking b minus a, so 5 minus 1, over the number of subintervals n, which is 4. My delta x is going to be 4 over 4, which is 1. So recall that each one of those intervals had a length of 1. So now my grid points are easy to find. We always start with x sub 0, which is our a value. In this case, our a value is 1. Our next grid point, which would be x sub 1, comes from taking our x sub 0 and adding in our delta x. So my next grid point is going to be 2. So x sub 2, the way we get it is we take our previous x sub 1 and we add in our delta x, which was 1. So 2 plus 1 would be 3. X sub 3 is going to be 3 plus our delta x, which is 1. So that gives me 4. And then my x sub 4 is going to be 4 plus 1, which is 5. Looking on our graph, this would be our x sub 0 is at 1. Remember, that's our a value. And then x sub 1, x sub 2, x sub 3, x sub 4, and x sub 5, which is our b value. Each one of these delta x's is 1. So if you have your a value, your starting point, and you have your delta x, to find your grid points, you just start with your a value, and in this case you're adding your delta x, which is 1, and that would get you to your next value, which is 2. If you add your delta x, which is 1, you get to 3, and so on. So that would be algebraically how you find all your grid points. Or you could use the formula that's given. I rarely use that formula. All I do is start with the first grid point, the x sub 0, and then I just keep adding delta x to my grid points. In example 2, what we're going to do is we're going to estimate the area under a graph. And here our graph is x squared. I'm going to go from x is 0 to x is 3. I'm going to use left endpoints with 6 subintervals. Okay, so let's put all this together. My x sub 0, that would be a is 0, b is 3. I need my delta x. So delta x is going to be b minus a, so 3 minus 0, over n. N is the number of subintervals, and here n is going to be equal to 6. So it's 3 minus 0 over 6, which is just 3 over 6, or 1/2. So that's my delta x. My grid points, I always start out with x sub 0 is equal to my a value, and in this case my a value is 0. So to get my next grid point, what I do is I take my delta x of 1/2 and I add it to 0. So x sub 1 is equal to 1/2. And then x sub 2, I get that from adding my delta x of 1/2 to my x sub 1, which is 1/2, to get 2 over 2, which is 1. X sub 3, add in my half, which would give me 1.5, or 3/2. X sub 4, add a half to get 4 over 2, which is just 2. X sub 5 is going to be 2.5, which is 5/2. And then my last grid point would be x sub 6, because I have 6 subintervals, and that's going to be 6 over 2, which is just 3. So notice I don't even have a graph, but I can still estimate the area under the curve x squared from x is 0 to x is 3 by just finding my grid points and knowing that the area with left endpoints, and I have 6 of them, is going to be 1/2 my delta x, right, times f of 0. Maybe I should write that out as f of 0 plus 1/2 times f of, my next grid point is 1/2. Okay, again, these are left endpoints. So when you do left endpoints, you always start with the first, the x sub 0. And I need 6 of these, right? So I'm going to go 1, 2, 3, 4, 5, 6. That's where I'm going to stop. Plus 1/2 f of 1 plus 1/2 f of 3/2 plus 1/2 f of 2 plus 1/2 f of 5/2. Okay, so these are the areas of 1, 2, 3, 4, 5 of my 6 rectangles. But notice that since this is a regular partition, our delta x, which is just the base of our rectangle, I can factor that out. And what's left over is just going to be f of 0, which is 0, right? We're putting it into our function, plus f of 1/2, so 1/2 squared is going to be 1/4, plus f of 1 is just 1, plus f of 3/2 is going to be 9/4, plus f of 2 is 4, plus f of 5/2 is 25 over 4. And that's just going to be 55 over 8. I actually did the math instead of plug this in my calculator. And then it's actually not an approximation if I write it in the decimal form because it's exactly 6.875. So that would be the approximate area between the function x squared and the x-axis from 0 to 3. So just a quick sketch of what this is. Okay? So our function is x squared. We're going to go from 0 to 3. So it's going to be something in here where we partition it all off. So we're estimating that this area from 0 to 3, that area is approximately 6.875 using left endpoints. As we saw in our first example, maybe the left endpoint is not the most accurate. Okay? Maybe it would be a midpoint. So let's move on. And we're going to be introduced to the Riemann sum. The Riemann sum is going to be, when we get into the next section, it's going to be how we define our integrals formally. So first of all, this definition, all it's doing is it's saying, okay, so you have this interval, you have some function. You're going to partition it into n subintervals of equal length of delta x. And let's say this x sub k star is any point in any of your intervals. Then, to compute the area, or approximate the area, we just add the height and the length, and the height and the length of all these rectangles. So we're just adding up the area of all these rectangles. And that's what we call a Riemann sum. The sum of these areas of rectangles on some interval AB. So our left Riemann sum would be if this x star is the left endpoint in the interval. A right Riemann sum is if our x star is the right. And the midpoint Riemann sum is if this x star is the midpoint. So it's somewhere inside this interval. Again, this is just notation. I wouldn't get too hung up on it. In example 3, we're going to estimate the area under the curve of sine of x from 0 to pi. And we're going to use right Riemann sums with 4 subintervals. All right, so my interval is going from 0 to pi, right? So here my a is the 0, my b is pi. So to figure out my delta x, it's going to be b minus a over n, where n is 4 because we're going to partition this into 4 subintervals. So my delta x is pi over 4. And we're going to use the right Riemann sums. Okay. So remember, we always start out with x sub 0, which is equal to our starting value a, and that's 0. And then we just add our delta x. So I'm going to add pi over 4 to 0 to get my next grid point, which is pi over 4. And then the next grid point, x sub 2, that's going to be equal to pi over 4 plus pi over 4, so that's 2 pi over 4, or pi over 2. And then x sub 3 is going to be pi over 2 plus pi over 4. That would be 3 pi over 4. And then x sub 4, which is my last grid point, would be 3 pi over 4 plus pi over 4, which is pi. So I have these grid points. I'm going to be using right endpoints, which means I'm going to start at x sub 1, then x sub 2, x sub 3, and x sub 4. So these would be the right endpoints in each one of my intervals. So to compute the area, or the approximate area underneath the curve of sine of x and the x-axis, it's going to be my delta x times all these heights. So I'm just going to factor out the pi over 4 because I know I can. And then just add up f of pi over 4 plus f of pi over 2 plus f of 3 pi over 4 plus f of pi. This is pi over 4 times sine of pi over 4 is square root 2 over 2 plus, if I put in pi over 2, sine of pi over 2 is 1, plus sine of 3 pi over 4 is square root 2 over 2, plus sine of pi is 0. So if I were to add all of these up, I get pi over 4 times 1 plus the square root of 2. In my calculator, that's approximately 1.896. So we're actually just building up on all our notation. Our goal is to eventually define these Riemann sums, or these integrals. Let's at the next section. So before we can formally define a Riemann sum, what we want to talk about is this sigma notation. So sigma is this symbol here. It's the Greek letter sigma, and we let it stand for sum. So we're going to sum, or we're going to add whenever we see this sigma. If you work with Excel spreadsheets, you're probably very familiar with this sigma, which means to sum. looking at this first expression, which is the sigma, or we're going to sum from a k value of 1 to a k value of 5. We're going to sum these k's. So what this means is we're going to put in 1 for k, and then we're going to add, the next k value is 2, so we're going to put in 2 for k, and we're going to add the next k value of 3 plus 4, and then we're going to end at 5. So if I were to sum 1 plus 2 plus 3 plus 4 plus 5, that's equal to 15. So let's try another one. We're going to start at k is equal to 1. So this sum is equal to, I need to put in 1 for k, so that's 1 squared, plus I put in 2 for k, and I get 2 squared, plus 3 plus 4, and I'm stopping when k is equal to 5. So the last term would be 5 squared. So when I add all this up, it's 55. Let's do one more example. I'm going to start with 1. K is equal to 1. This sum of 1 over k is going to be 1 over 1 plus 1 over 2 plus 1 over 3 plus, and now I have a problem because I'm not stopping at a specific number. This is just a sum for any number n. So the way we show that is we say, okay, this pattern will continue, plus the last thing I'm going to add is 1 over n, whatever that n may be. So I really can't add those all up because I don't know what n is. So now that you're familiar with this notation, this summation notation or this sigma notation, I'd like to look at some formulas for summations. In this first formula, it says if you're summing a constant number, then it's going to be equal to that constant number times whatever n value you're going to. So for example, if I was going to sum from k is equal to 1 to 4 of 2, think about what that's saying. Notice that there's no k value in this summation, it's just the number 2. So when k is equal to 1, I have 2, plus when k is equal to 2, it's still just 2, plus when k is equal to 3, it's 2, plus when k is equal to 4, we have 2. And then 2 plus 2 plus 2 plus 2 is actually just 2 times 4, which is 8. Okay? So again, whenever you have just a constant number in your summation, you just multiply your n value where you end with your constant. The next formula we look at is the one that we had previously looked at. And that says that if the summation is just k, then whatever n you're going to, you don't actually have to expand it all out and add it. You could just use this formula that says it's n times n plus 1 over 2. So let's just verify with our previous example. So remember, we were looking at the sum from k is equal to 1 to 5 of k. Remember, we said that was equal to 15. If I was to use this formula, my n is 5. So we have 5 times 5 plus 1 over 2. Is that equal to 15? Well, 5 times 6 is 30, divided by 2, it's 15. Okay? So this formula checks out. And you're free to use all these formulas. Another one we had looked at earlier is k squared. And this formula says that whatever your n value is, it's n times n plus 1 times 2n plus 1 over 6. So again, we really didn't have to expand out our previous example where we computed from k is equal to 1 to 5 of k squared. We could have just used this formula and said, oh, okay, n is 5, so it's 5 times 5 plus 1 times 2 times 5 plus 1 all over 6. So that's going to be 5 times 6 times 11 over 6. That should turn into 55, and it does. So what we haven't used previously is k to the third power. So for whatever n you're going to, k to the third is going to be n squared times n plus 1 squared over 4. Now we have these properties when we're looking at summations. One of the properties, and we'll use this quite a bit, is that if you just have a constant number times whatever the term is or the expression is, you can always pull that out to the front of the summation and then multiply by that value later on. If you're adding or subtracting two expressions in your summation, you can break it up into two different summations. Let's use this property to evaluate this summation. Now I could just expand it out, put in k is equal to 1, 2, 3, and 4, and then figure out what the sum is. Or I can notice that by these properties there is a subtraction, so I could split it up into two sums, where the first is 5k minus, and the second one would be the number 3. However, this first sum, that 5 is a constant that I could bring out in front of my sum. And then the 3, again, is just some constant that I could bring out, right? So this piece here, since it's just a constant, it's going to be equal to 3 times 4. This here, I have a 5. But I have a formula for k, right? Remember, my n is 4, so it's going to be 5 times 4 times 4 plus 1 over 2. So the 4 times 5 would be 20 over 2 is 10. And this is 5 times 10, which is 50 plus 12, which would be 62. So again, we can just use all those properties of summations to break things up into smaller and smaller pieces. So why did we even have to discuss these? Well, we're going to go to our Riemann sums. And instead of looking at the addition of all these rectangles, we're going to shorten our notation, because all we're doing here is summing up these areas of rectangles. So instead, we're going to replace it with summation notation. These mean the exact same thing. So our x star, that's just some point in each one of our intervals, which would give us the height of our rectangle. And our delta x, that's just the base of our rectangles, or the length of those partitions. So now when we look at our left, right, and midpoint Riemann sums, what we're going to do is we're going to define what this x star is. So if we use left Riemann sums, the x star, which would be the left endpoint on the interval, can be computed by a plus k minus 1 times our delta x. Our right Riemann sum, the x star, is going to be equal to a plus k times delta x. Ooh, that seems like the nice one. And then the midpoint Riemann sum, our x star, is going to be a plus k minus 1/2 times delta x. So how do we use all this to compute areas? Well, we're going to go ahead and figure out the right, the left, and the midpoint Riemann sums. We have our function. F of x is going to be the square root function. I have my interval from 1 to 4, so a is 1, b is 4. I'm going to use 6 subintervals, so n is 6. So let's start with the right Riemann sum. But before I do that, I need to figure out what my delta x is. So delta x is b minus a, which is 4 minus 1, over n is 6. So divide by 6, and I get 3 over 6, or 1/2. Let's look at our grid points. Our x sub 0 is that a value, which is 1. To get x sub 1, what we're doing is we're adding 1/2. So that's going to be 3/2. I think I'm going to write these as decimals so I can just plug stuff in a calculator. It'll be easier. And then my x sub 2 means I'm going to add 1/2, or 0.5. So x sub 2 is 2. X sub 3 is going to be 2.5. X sub 4 is going to be 3. X sub 5 is going to be 3.5. And then our x sub 6, because we have 6 intervals, is going to be 4, which is our b value. So I have my delta x. I have all my grid points to figure out my right Riemann sum. I want to first figure out what this x sub k star is. By the above formula, it's going to be 1 plus k times delta x, which is 0.5. Okay, so again, I'm using the right Riemann sum first. That's the easiest one. So what we're going to do with that is when we compute our Riemann sum of 6 subintervals using right endpoints, it's going to be equal to, we're going to look at the sum that we have above. The sum from k is equal to 1 to our n is 6. It's going to be f of our x star, which is 1 plus, I think I want to put the 0.5 in front of the k because it bugs me to have a number after a variable. And then we're going to multiply that by delta x, which is 0.5. So we can use this summation to compute these approximations of areas using Riemann sums. Now, because the 0.5 is a constant, I can go ahead and pull that out, and then I'm going to multiply it by this sum here. I start with k is equal to 1. So this is going to be f of, when k is equal to 1, this is going to be 1.5. Plus f of, when k is equal to 2, this is 2 times 0.5, which is 1, so this is going to be 2. Plus f of 2.5 plus f of 3 plus f of 3.5 plus f of 4, which is going to be 0.5 times, this is the square root function, so the square root of 1.5 plus the square root of 2 plus the square root of 2.5 plus the square root of 3 plus the square root of 3.5 plus the square root of 4, which is just 2. So plugging this into a calculator, and then don't forget that you need to multiply your result by that 0.5, that delta x. We get, oops, when I put in the calculator, it's an approximation of 4 point, I'll just go out 4 decimal places, 9115. Let's look at our left Riemann sum and figure out what our x sub k star needs to be. So our left Riemann sum, the x sub k star is going to be 1 plus k minus 1 times delta x, which is 0.5. I'm going to go ahead and distribute that 0.5 to get 1 plus 0.5k minus 0.5. And then I can go ahead and do the 1 minus 0.5 to write this as 0.5k plus 0.5. So that's the x sub k star that I'm going to be putting in my Riemann sum. So the left endpoints with the 6 subintervals is going to be the sum from k is equal to 1 to 6 of f of 0.5k plus 0.5, and then we multiply by our delta x, which is 0.5. So again, I'm going to move my delta x out in front because I can. And now put in 1 for k. This becomes 0.5 plus 0.5, which is 1. So it's f of 1. So I'm going to skip a step, and f of 1 is the square root of 1 plus, putting in 2 for k, I get 1 plus 0.5, which is 1.5. And this would be the square root of 1.5. When I put in 3 for k, I get 1.5 times 0.5, which is 2. So the square root of 2. And so on. So this is the square root of 1, square root of 1.5, square root of 2, square root of 2.5, square root of 3, square root of 3.5. And then putting that in a calculator, I get approximately 4.4115. Okay, so they're kind of close, the right and the left. Let's try the midpoint. So when I figure out my x sub k star, it's going to equal to 1 plus k minus half but I'm going to write a half as 0.5, easier for me to put in my calculator, times delta x, which is 0.5. I'm going to clean this up by distributing the 0.5 to get 1 plus 0.5k minus 0.25. So the 1 minus 0.25 would be a 0.5k plus 0.75. All right, so that's going to be my x sub k star that I'm going to be putting in to my sum. So m sub 6, it's going to be the sum from k is equal to 1 to 6 of f of 0.5k plus 0.75 times our delta x, which is 0.5. So again, I'm going to pull the delta x out in front. When k is equal to 1, it's 0.5 plus 0.75, which is 1.25, and f of 1.25 is the square root of 1.25, plus k is equal to 2, we get 1.75, so the square root of 1.75, plus, when k is equal to 3, I get 2.25. When k is equal to 4, I get 2.75. K is equal to 5, I get 3.25. And then when k is equal to 6, I get 3.75. So again, putting all of this inside the calculator, I have 4.6692. So I needed to make a conjecture about the area under the curve. When I look at all three values that I have about 4.9, 4.4, and 4.6, or 7. So my conjecture is going to be the middle value, which I got from the midpoint Riemann sum. So my conjecture is that the area is going to be closest to 4.6692. So typically you would choose the middle value. So we've been looking at partitions like 4 subintervals or 6 subintervals. But what happens if you want to take something and partition it into, say, 10 or 20 or 30 subintervals? That would be ridiculous to write out in a long way. So what you're going to do is use your calculator. And with the TI-84, you would hit the math symbol on your calculator and then scroll down to summation. Once you enter summation, you're going to get this summation symbol, and you'll have these boxes underneath where you can enter in your k values, the starting, the ending, and you can put in your function or what you want to sum. Just a note here that it's probably easier to use x as your variable instead of trying to use k. So you could put, say, x is equal to 1 to whatever your n value is, 20, right? And then enter in whatever you want to sum here. If you're not fortunate enough to have the TI-84 and you're using the old TI-83, it may be a little bit more difficult for you. So in the TI-83, you would hit second stat and then choose math and then sum. So that will give you this piece that'll show up on your screen at the end. And then you're going to go back in and do second stat ops for operation, and the operation is sequence. So this will show up. What you're going to have to do is enter all this stuff with the 2 parentheses to end the expression. So what is all this stuff? Well, we already know what this piece is, right? This is the expression that we did on the previous page. That's what you're going to put into your calculator. You're going to put a comma, and you're going to tell your calculator that you want to sum over the x's starting with 1, and then if your n is 20 or 30, that's what you would put in here. So you're going to start with x is equal to 1. You're going to end at this n value, which let's just say it's 30. Now this last number here, you want to put in a 1, because that tells your calculator that I'm going to start with x is equal to 1, and then I'm going to go to the next x value of 2. If you change that last number to say 2, what it's going to do is it'll start at 1, and then it's going to go to x is equal to 3, and then x is equal to 5. So you don't want it to skip values, skip x values. So that would be the worst case scenario if you were using your calculator to sum. But let's look at example 6. We want to evaluate the right, left, and midpoint Riemann sums, and we're going to go back to our square root function. We're looking at the same interval from 1 to 4, but this time notice my n value is actually 60. Okay, so again, I don't want to expand that out. That's just crazy. I want to use my calculator. So remember, our delta x is b minus a over n, so that's going to be 4 minus 1 over 60, which is just 3 over 60. And 3 over 60 is 1 over 20. Since I'm putting this in my calculator, I don't like putting fractions in my calculator. I like decimals better, so I'm going to write 0.05 for my delta x. Now, if I had a repeating decimal, then I would not use the decimal form. You want your summation to be as accurate as possible. So if it's a repeating decimal, keep it as a fraction. So we're going to use the midpoint Riemann sum. And, oh, I'm sorry, you can ignore this last thing about making a conjecture. We're not going to make a conjecture, because we're just going to look at the midpoint Riemann sum, since that's the most difficult one to compute. So on the TI 84, you're going to get to hit math, then summation, and you're going to get to this summation here. You're going to enter in x is equal to 1, and then we're going to go to 4, right? Because that's my starting x value, and that's my ending. Oh, sorry, not 4. I don't have 4 anymore. I have 60. That's my n. We're going to look at f of, now computing our midpoint Riemann sum will end up being 0.05x plus 0.975. Times my delta x. How did I get that midpoint? Well, remember that my x sub k star is equal to 1 plus, in parentheses, k minus 1/2, or 0.5, times delta x, and in this case my delta x is 0.05. Distributing the 0.05, I have 0.05k minus 0.5 times 0.05 is going to be 0.025. And that's how I got that x sub k star that I put in my function. This is going to be 0.05k plus 0.975. So that would be here. So in your calculator, you're going to start with 1, you're going to end with 60. In place of the f of 0.05x plus 0.975, you're going to put the function, which is the square root function of 0.05x plus 0.975, and you're going to multiply that by your delta x. That's what you'll enter into your TI-84 calculator. So what you should get is this approximation of 4.6667. Now if you were using the TI-83 and you had one of the older models with the old software, this is the worst case scenario. You're going to enter in those keystrokes so that you get sum, parentheses, sequence, parentheses. So that's telling your calculator to sum or to add the following sequence. And your sequence will be your function, which is the square root of 0.05x plus 0.975, right? So that's your f of x sub k star, but then you're going to multiply that by 0.05, your delta x, comma, tell your calculator to use the x values to put in your numbers from 1 through 60. You're going to start with an x value of 1. You're going to end with an x value of 60. And increments of counting will be 1. And now you have to do double parentheses to close all of this. Once you enter that in your calculator, you should get the same value, 4.6667. All right, so that ends our 5.1. The notation's a little crazy, and this can get a little tedious when you do your summations, but I wouldn't worry too much about this. This is just the basics, and then we'll talk about the formal definition of an integral in the next section.